To find the horizontal asymptotes of a function, if it has any, we must evaluate the function's limits at positive and negative infinity. We're going to do these 7 examples looking at each of these functions and determining if they have any horizontal asymptotes. This video has chapters, so you can skip around the problems as you please. So again, we say that the line y equals L is a horizontal asymptote of f if the limit of that function f as x goes to infinity is L, or if the limit as x goes to negative infinity is L. Either way, y equals L functions as a horizontal line that the function will get arbitrarily close to. Let's begin with this first example. F of x equals x squared minus 1 divided by x squared plus 1, and we're trying to find its horizontal asymptotes. So we need to consider the limit of the function as x goes to infinity, and the limit of the function as x goes to negative infinity. It may be that this function has 2 different horizontal asymptotes. It could also be that it has just one, or it may have none at all. One way to evaluate this limit is to just realize that as x gets really big, so too does x squared. And so minus 1 and plus 1 really don't do anything. We could just ignore those and say, clearly the limit is going to approach 1. It's going to approach x squared over x squared, which is just 1. But we can make that argument more formal by dividing the numerator and denominator by x squared. Dividing the numerator by x squared gives us 1 minus 1 divided by x squared, and dividing the denominator by x squared gives us 1 plus 1 divided by x squared. This is more clearly equal to 1 because as x goes to infinity, this term clearly goes to 0, and this term clearly goes to 0. So we're just left with 1 over 1. Hence, this limit does equal 1, as we would expect. We can use the exact same argument as x goes to negative infinity. Nothing would change. Of course, the x's here are squared, so we actually just have positives, even in the negative infinity case. So also, as x goes to negative infinity, this function approaches 1. That means there's just one horizontal asymptote, the horizontal line y equals 1. So the horizontal asymptote of this function is y equals 1, and we can see that in this picture. To the left, the function is getting arbitrarily close to that horizontal line y equals 1, and that's also what it's doing to the right. Now for our second example, f of x equals arctan x. To find its horizontal asymptotes, we must evaluate its limits at positive and negative infinity. We must understand how arctan works. As the input of arctan x goes to infinity, arctan is going to approach whatever value would make tangent go to infinity. Now, tan x is infinity at 2 places in particular. That's at pi over 2 and at negative pi over 2. This is because tangent, you may remember, is sine x over cosine x. And cosine x is 0 at both of these values. So at pi over 2 and negative pi over 2, the tangent function is undefined. And as we approach these values, tangent goes to infinity or negative infinity. Because sine is positive as we approach pi over 2, tangent goes to positive infinity as x approaches pi over 2. Hence, as x approaches infinity, arctan of x goes to pi over 2. On the other hand, as x approaches negative pi over 2, sine x is negative, and so tangent would approach negative infinity. So as x goes to negative infinity, arctan of x goes to negative pi over 2. So that's an example you've really got to know your trig for. The horizontal asymptotes of arctan x are y equals pi over 2, which we see here in the graph, and y equals negative pi over 2. So this is an example of a function with 2 distinct horizontal asymptotes. This next example is very easy. F of x equals 1 over x. What are the horizontal asymptotes of this function? Well, the limit of 1 over x as x goes to infinity clearly is 0. As x gets really big, this is going to get closer and closer to 0. Same thing as x goes to negative infinity. As x goes to negative infinity, 1 divided by x, again, is going to get arbitrarily small. It's going to approach 0. And so there's just one horizontal asymptote for this function. The horizontal asymptote is y equals 0, and you can see that here in the graph. To the right, it is approaching y equals 0, and to the left, as we go to negative infinity, it is also approaching y equals 0, which is the x-axis. Here's an example more like the first one. F of x equals 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. In this example, we could think about it like this. X squared is going to be growing a lot faster than minus x, 4x, minus 2, and plus 1, of course, aren't growing at all. So in this way, the dominant terms are these ones of highest degree, 3x squared and 5x squared. So we could say, well, as x gets really big, the only terms that really matter are these ones, 3x squared and 5x squared. Their ratio is 3/5, and so that would be the limit. This logic is sound, but there is a more formal way to describe it. Just as in the first example, we can divide by that highest degree term, x squared. Divide the numerator and denominator by x squared, and that gets us here. In the numerator, we have 3 minus 1 over x minus 2 over x squared. Dividing the denominator by x squared gives us 5 plus 4 divided by x plus 1 divided by x squared. Now it's clear as x goes to infinity, all of these terms that we previously disregarded indeed approach 0. And so the limit, well, we're just left with 3/5. And that's the ratio of the coefficients of those leading terms. Now, as x approaches negative infinity, nothing changes. It still just goes to 3/5. These terms zero out, so that's what we were left with. There's just one horizontal asymptote. This is a graph of the function, pretty wacky looking. You can see that as x goes to negative infinity, it's approaching 3/5, and as x goes to positive infinity, it's approaching 3/5. That is the one horizontal asymptote of this rational function. In general, it's very easy to find the horizontal asymptotes of a rational function. A rational function is any function like this, some polynomial divided by another polynomial. Here's how to deal with those in general. If we have a rational function that's a polynomial p of x divided by a polynomial q of x, and let's say the leading term of p of x is px to the n, and the leading term of q of x is qx to the m. Then, if those degrees, those highest degrees in the polynomials, are equal, the horizontal asymptote of the function is just going to be the ratio of the coefficients of those highest degree terms. That's just like we saw in the previous example. The degree of each polynomial was 2, and so the horizontal asymptote just ended up being the ratio of the coefficients of those leading degree 2 terms. On the other hand, if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is going to be y equals 0, because in this case, the denominator will outpace the numerator, so it's going to end up approaching 0 overall. On the other hand, if the degree of the numerator is greater than the degree of the denominator, f of x will have no horizontal asymptote because the numerator is just growing too quickly. Here's an example that's similar to those rational functions, but a little bit different. F of x equals 3x minus 2 divided by the square root of 2x squared plus 1. One way to think about this is that as x gets really big, this plus 1 really isn't doing anything, so we could just ignore it, and in the denominator, we would have the square root of 2x squared, which is the same as the square root of 2 times x, at which point it's clear the numerator and denominator have the same degree, and so we could just look at the ratio of those leading coefficients, 3 over root 2. This is the correct answer, but again, there is a more formal way that we could go through this process. We're going to divide the numerator and denominator by x. That's the highest power of x. The that appears in this function. You may say, well, hey, look, x has a power of 2 in the denominator, but it's in a square root, so really it's like a power of 1. So we're dividing by that highest power. Divide by x, divide by x. But note that when x is positive, which is what we care about right now, x is equal to the square root of x squared. So when we divide the denominator by x, just to make it compatible with the square root, we're going to divide by x squared in that square root. 3x divided by x is 3, and negative 2 divided by x is negative 2 divided by x. In the denominator, we divide by x, which is the same as dividing by the square root of x squared, so we're dividing the inside of this square root by x squared. 2x squared divided by x squared is 2, and 1 divided by x squared is 1 divided by x squared. At this point, it's clear as x goes to infinity that minus 2 over x approaches 0, and 1 over x squared approaches 0. Hence, the only stuff that's left is the 3 divided by root 2, which, if you want to rationalize the denominator, you could multiply by root 2 over root 2 and get this as the final answer. But of course, this all just applies for x approaching positive infinity. In the case where x approaches negative infinity, the only change we'll make to our strategy is to note that now x is negative, and so x isn't equal to the square root of x squared. Rather, x is equal to negative square root of x squared. But again, we're going to divide the numerator and denominator by x, but in the denominator now we're thinking of it as negative root x squared. So then the numerator is the same as before, and the denominator is as well, except we have that factor of negative 1. We can bring that negative out, and again as before, we still have that 3 over root 2. We could rationalize the denominator, and we get this second horizontal asymptote, negative 3 root 2 over 2. There is a graph of the function, and we can see its horizontal asymptotes, positive 3 root 2 over 2 as x goes to positive infinity, and it's approaching negative 3 root 2 over 2 as x goes to negative infinity. Next, f of x equals the square root of x squared plus 1 minus x. As x goes to negative infinity, it's clear that this function just diverges to positive infinity, because certainly the square root would be a positive number, and then we are subtracting x. But remember, in this case, x is negative as x goes to negative infinity. So we would just be adding an arbitrarily large number to this positive number. It would diverge to positive infinity. So we're left to consider what happens when x approaches positive infinity. In that case, this function may indeed have a horizontal asymptote. In order to ascertain what this is, we're going to multiply and divide by the conjugate of this expression, which is a strategy you may remember from some of our early examples of evaluating limits. The conjugate of this minus this is this plus this. And when we multiply by the conjugate, we get the difference of squares, which will cancel out that square root. So this limit is going to be the same as this one, where we have just multiplied and divided by the conjugate. Of course, multiplying and dividing by the same thing does not change the value of the expression. But then we're going to leave this conjugate in the denominator, but this multiplied by its conjugate, like we said before, produces the difference of squares. This term, squared, is x squared plus 1, just canceling out the square root. And then this term, squared, is just x squared. So we have minus x squared. The middle terms cancel out because of the minus and the plus. X squared minus x squared, of course, cancel out, so we're just left with 1 divided by that sum. That gets us here, and to finish evaluating this limit, we can divide the numerator and denominator by x. So in the numerator, we have 1 divided by x, and in the denominator, we can divide in the square root by x squared. So x squared divided by x squared is 1, and 1 divided by x squared is 1 over x squared. And then, of course, we have this plus 1, since x divided by x is just 1. Now, as x goes to infinity, it's clear that this goes to 0, so the denominator is actually approaching root 1 plus 1, or 2, and the numerator is just approaching 0. Hence, this is 0 divided by 2, or just 0. So the one horizontal asymptote of this function is y equals 0, and we can see that here in the graph. As x goes to negative infinity, the function gets arbitrarily large, but as x goes to positive infinity, the function approaches that horizontal asymptote of 0. One last quick example is f of x equals e to the x. Hopefully you know as x goes to positive infinity, e to the x just gets arbitrarily large. That limit is infinite. As x goes to negative infinity though, e to the x is the same as 1 over e to the absolute value of x. Of course, x in this case is negative, but if we move it to the denominator, that exponent can become positive, so we put it in absolute value bars. Now, as this exponent of x goes to infinity, this is going to approach 0 because the denominator is just getting arbitrarily large, while the numerator is just 1. So this would approach 0, and that is a horizontal asymptote of e to the x. And that is a hopefully familiar graph of e to the x. To the right, it goes to positive infinity, and to the left, it approaches 0. But those are a few examples of finding horizontal asymptotes of functions by taking limits at infinity. Let me know in the comments if you have any questions, and be sure to check out my Calculus 1 course and Calculus 1 exercises playlists in the description for more.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what